Right now, nearly 2 billion miles from Earth, a planet is spinning the wrong way, not slightly tilted, not gently wobbling. Uranus rolls through space like a barrel, its north pole pointing almost directly at the sun. Imagine waking up one morning and watching the sun rise in the north, climb straight overhead, then set in the south. Now imagine that morning lasting 42 years. You live on a world where seasons make sense. Summer, winter, the gentle 23-degree tilt that gives Earth its rhythm. But what if your planet got knocked sideways? What if something hit it so hard that day and night stopped meaning anything, and your world became a rotisserie, slowly cooking one hemisphere while the other froze in eternal darkness? This isn't science fiction. This is Uranus. And it's not alone. Across our solar system and beyond, astronomers are discovering worlds that spin on their sides, upside down, or at angles so extreme they challenge everything we thought we knew about how planets form. The question isn't just, how did this happen? It's far more unsettling. Could it happen again? By the end of this journey, you'll understand exactly why these sideways worlds hold the key to one of planetary science's deepest mysteries, and why some scientists believe Earth itself narrowly escaped the same fate. To understand rotisserie planets, you first need to forget everything intuitive about up and down in space. When our solar system formed 4.6 billion years ago, a massive disk of gas and dust swirled around the young sun. Everything spun in roughly the same direction. Planets coalesced from this disk, and physics dictated they should all rotate the same way, with their axes perpendicular to their orbits. Neat. Orderly. Predictable. Then Voyager 2 arrived at Uranus in January 1986, and orderly went out the window. The spacecraft found a world tilted 97.8 degrees. Not a slight lean. The planet essentially orbits on its side, with its rings and moons circling vertically like a target around a bullseye. Dr. Heidi Hammel, planetary astronomer and Voyager team member, described the encounter as like nothing we'd ever seen, a planet that had been knocked over and just kept rolling. The implications were staggering. At Uranus, the sun doesn't rise and set daily the way you experience it. Instead, during summer at the North Pole, the sun spirals slowly toward the zenith over 21 years, hangs there, then spirals away for another 21 years. Meanwhile, the South Pole experiences 4 decades of unbroken night. One pole bakes. The other freezes. Then they switch. This creates weather patterns that exist nowhere else in the solar system. Voyager found surprisingly calm atmospheres where scientists expected chaos. The James Webb Space Telescope, observing Uranus in 2023, revealed something even stranger: massive polar storms appearing as the planet approaches its 2049 solstice, when the North Pole will point directly at the Sun for the first time since Voyager's visit. But Uranus is just the beginning. Venus rotates completely upside down, spinning backward compared to every other planet. Exoplanet surveys suggest that wildly tilted worlds may be common throughout the galaxy. And the mechanism that created these rotisserie planets, catastrophic ancient collisions, tells us something profound about the violent chaos that shaped our cosmic neighborhood. The story of sideways worlds isn't just about distant ice giants. It's about the cosmic dice roll that determined whether your planet would have gentle seasons, or 42 years of darkness, and it starts with a collision so violent, it rewrote the rules of planetary physics. For 2 centuries, Nobody knew Uranus was broken when William Herschel spotted the pale blue disk through his homemade telescope in 1781. He thought he'd found a comet. It took months of observation before astronomers realized this was something far more significant, the first planet discovered since antiquity. But Herschel's telescopes couldn't reveal the world's deepest secret. Uranus appeared as little more than a fuzzy dot, its extreme tilt invisible to 18th-century instruments. The first hints came in 1851, when William Lassell observed that Uranus's moons orbited in a plane nearly perpendicular to the solar system. Astronomers noted the oddity, filed it away, and moved on. The mathematics of orbital mechanics were still being written. Strange tilts seemed like curiosities, not crises. Then came the 20th century, and with it, the uncomfortable question no one could answer. By the 1960s, planetary scientists had developed sophisticated models of solar system formation. The nebular hypothesis explained beautifully how planets condensed from the same spinning disk of material. Every world should rotate in roughly the same direction, with axial tilts of just a few degrees. Mercury, Venus, Earth, Mars, Jupiter, Saturn, all seemed to fit the pattern, give or take. Uranus didn't fit at all. Dr. Harold Levison, planetary dynamicist at the Southwest Research Institute, describes the problem bluntly. Uranus was an embarrassment to our models. Here was this giant planet, 4 times Earth's diameter, and it was rolling through space like someone had knocked it over. Our equation said that shouldn't happen. The solution seemed obvious. Something hit it. In the 1970s and 80s, computer simulations grew powerful enough to model catastrophic collisions. The scenario was dramatic but plausible. Early in solar system history, when planets were still forming, a protoplanet roughly the size of Earth slammed into young Uranus at a shallow angle. The impact delivered enough angular momentum to tip the entire world onto its side. One collision. One cosmic accident. Mystery solved. Voyager 2's 1986 flyby seemed to confirm the theory. The spacecraft revealed Uranus as a world frozen in aftermath, bland atmosphere, minimal internal heat, a planet that looked like it had been traumatized and never recovered. Scientists published papers. Textbooks were updated. The case appeared closed. But no one had looked closely enough at the moons. Here's the problem that shattered the elegant solution. If a single giant impact knocked Uranus sideways after its major moons had formed, those moons should still orbit in the original plane. They'd circle the planet's equator as it existed before the collision, perpendicular to its current tilt. Instead, Miranda, Ariel, Umbriel, Titania, and Oberon all orbit perfectly aligned with Uranus's tilted equator. The moons followed their planet when it fell over. This is gravitationally impossible for large, distant moons. Dr. Robin Canup, whose computer simulations revolutionized impact theory, ran the numbers repeatedly. A single impact can tip the planet, she explains, but it can't drag the entire moon system with it. The physics simply doesn't work. Suddenly, the simple answer wasn't simple anymore. Either the moons formed after the impact, which contradicted their ancient, heavily cratered surfaces, or something far more complex had happened. The single impact theory had explained the tilt beautifully, while explaining nothing else. Scientists were back to zero. And the deeper they looked at rotisserie planets across the solar system, the stranger the picture became. because Uranus wasn't the only world hiding secrets about its violent past. Venus broke everything while astronomers puzzled over Uranus's sideways spin. Radar observations in the 1960s revealed something even more disturbing about Earth's so-called twin. Venus doesn't just tilt strangely, it rotates completely backward. Stand on its surface, and you'd watch the sun rise in the west, crawl across the sky over 116 Earth days, then set in the east. A day on Venus lasts longer than its year. This isn't a minor tilt. Venus spins at 177.3 degrees, essentially upside down. And unlike Uranus, there's no dramatic moon system to constrain theories. Venus has no moons at all. It's a world that erased its own evidence. Dr. Alexander Correa, planetary scientist at the University of Aveiro, has spent decades modeling Venus's bizarre rotation. His conclusion is unsettling. We cannot determine what happened. The same final state can be reached through completely different pathways. Venus keeps its secrets. The pathways themselves reveal how little we understood. Point 1 scenario. A Uranus-style giant impact flipped Venus completely over. Another, gravitational tides from the Sun gradually slowed and reversed its spin over billions of years. A third, chaotic interactions with other planets during the solar system's violent youth. Each model produces a backward-spinning Venus. None can be proven. None can be eliminated. But the real turn came when scientists stopped asking what knocked these planets over, and started asking a far more troubling question. What if nothing knocked them over at all? In 2012, Dr. Alessandro Morbidelli and his team at the Nice Observatory published simulations that shattered the collision consensus. Their models showed that during planetary migration, the chaotic period when Jupiter and Saturn shifted orbits and scattered smaller bodies throughout the solar system, gravitational interactions alone could produce extreme axial tilts. No impacts required. The math was elegant, disturbing, and reproducible. Giant impacts are dramatic, Morbidelli explains. They make good stories. But gravitational perturbations during planetary migration can tilt worlds just as effectively, and they leave no craters, no debris, no evidence. The implications rippled through planetary science. If migration could tilt Uranus, it could tilt anything. The neat categories, impacted worlds versus stable worlds, dissolved into probability clouds. Earth's modest 23-degree tilt, the foundation of our seasons and climate stability, suddenly looked less like cosmic design and more like cosmic luck. Meanwhile, the Uranus problem got worse. Dr. Takanori Sasaki at the Tokyo Institute of Technology proposed that Uranus experienced not one giant impact but several smaller ones. His 2019 simulations showed that a sequence of collisions, perhaps 3 or 4 objects, each 1 to 3 times Earth's mass, could tip the planet while also capturing its moons into their current orbits. The math worked beautifully. But it required extraordinary coincidence. Multiple impactors, hitting at just the right angles, at just the right times, over millions of years. Some scientists embraced the model. Others called it statistical special pleading. Dr. Robin Canup remains skeptical. Multiple impacts solve some problems but create others. We're explaining one unlikely event with several unlikely events. That's not progress, that's desperation. The debate continues today. unresolved, and then exoplanet surveys revealed something that made our solar system's rotisserie planets look ordinary. Worlds orbiting other stars showed axial tilts across the entire spectrum. Planets with seasons lasting centuries. Hot Jupiters spinning perpendicular to their orbits. The message from the galaxy was clear: sideways worlds aren't anomalies. They might be the norm. The breakthrough didn't come from a telescope. It came from a supercomputer in Boulder, Colorado. In 2021, Dr. Zeev Rogosinski at the University of Maryland ran the most comprehensive simulations ever attempted of tilted planet formation. His team modeled thousands of scenarios, impacts, migration, gravitational resonances, and combinations no one had tried before. The results unified decades of competing theories into something unexpected. There was no single mechanism. There never had been. We kept looking for the answer, Rogosinski explains. One cause, one event, one explanation. But planets don't work that way. Uranus probably experienced both impacts and gravitational perturbations. Venus probably experienced tidal evolution and chaotic interactions. These aren't competing theories, they're chapters in the same story. The synthesis reframed everything. Early solar system history wasn't a series of isolated catastrophes. It was a continuous cascade of violence, gravitational tugs destabilizing orbits, collisions reshaping worlds, tidal forces slowly warping rotations over hundreds of millions of years. Any planet could be tilted by any combination of mechanisms. Including Earth, the James Webb Space Telescope's exoplanet observations confirmed what simulations predicted. In 2023, JWST characterized the atmospheres of several tidally locked worlds, planets so close to their stars that one face burns in perpetual daylight while the other freezes in eternal night. These are rotisserie planets taken to extremes. Not tilted 90 degrees, but locked entirely, their rotation periods matching their orbital periods. Dr. Sarah Seeger at MIT sees these worlds as laboratories for understanding our own solar system survivors. Every tilted planet, every locked world, every backward spinner tells us something about planetary evolution. We used to think Earth's configuration was normal. Now we know it's just one outcome among many. The data reveals patterns. Small rocky planets tend toward tidal locking when close to their stars. Gas giants in wide orbits show random axial tilts, suggesting impacts dominate their histories. Ice giants like Uranus occupy a middle zone where both impacts and gravitational effects compete. But the most profound revelation concerns habitability itself. Earth's 23-degree tilt creates seasons that drive atmospheric circulation, ocean mixing, and evolutionary pressure. Too little tilt, and equatorial regions might overheat while poles freeze permanently. Too much tilt, and the climate swings between extremes that could sterilize continents. Venus's backward spin and absent tilt may have contributed to its runaway greenhouse, a world that might once have had oceans, baked into a hellscape partly because it rotated wrong. Dr. René Heller at the Max Planck Institute has modeled habitability across different axial tilts. His conclusion is sobering. The range of tilts compatible with complex life is surprisingly narrow. Earth sits comfortably within it. That comfort was never guaranteed. The open questions remain vast. We still don't know precisely what tipped Uranus. We can't determine whether Venus was flipped by impact or slowed by tides. Exoplanet tilts remain mostly unmeasurable with current technology. The James Webb Space Telescope can characterize atmospheres but cannot directly observe rotation axes. Future missions may help. NASA's proposed Uranus orbiter, ranked as the highest priority flagship mission in the 2023 Decadal Survey, would study the ice giant's interior, atmosphere, moons, and rings in unprecedented detail. Decades of close observation might finally reveal whether the tilt was sudden or gradual, single event or cumulative. Until then, scientists work with probabilities, not certainties, but the real question isn't what tilted these worlds. It's what their existence means for ours. 2 billion miles away, Uranus keeps rolling. It doesn't know it's broken. It doesn't know that astronomers on a small blue world have spent decades arguing about its wounds. It simply continues its 84-year orbit around the Sun, one pole slowly roasting while the other freezes, a world caught in perpetual slow-motion tumble that began before life on Earth crawled out of the oceans. And somewhere in that patient, silent rolling lies a truth we've been circling throughout this entire journey. We are here because our planet spins the right way. Think about what we've uncovered together. Uranus, knocked sideways by ancient violence we still cannot fully reconstruct. Venus, spinning backward through mechanisms that may never be proven. Exoplanets scattered across the galaxy showing every possible orientation, worlds where seasons last centuries, where one hemisphere burns while the other never sees light, where the very concept of day loses all meaning. The universe doesn't care about habitable tilts. Physics doesn't prefer gentle seasons. The forces that shaped our cosmic neighborhood, impacts, migrations, gravitational chaos, produced outcomes across the entire spectrum of possibility. Some worlds ended up temperate. Most did not. Dr. Carl Sagan understood this decades before our simulations confirmed it. "We live on a mote of dust suspended in a sunbeam," he wrote. But that mote of dust happens to tilt at exactly 23.4 degrees, not 0, not 90, not 177. Just enough to create seasons that drive circulation. Just enough to prevent permanent ice caps from swallowing continents. Just enough to give evolution the rhythms it needed to produce complexity, just enough. The James Webb Space Telescope continues scanning distant worlds, characterizing atmospheres, searching for biosignatures. But every discovery reinforces the same unsettling message. Habitability isn't just about distance from a star, or the presence of water, or the thickness of an atmosphere. It's about rotation. Orientation. The angle at which a world presents itself to its sun, and that angle, for most planets, is determined by violence. Here's what haunts planetary scientists when they consider Earth's history. 4.5 billion years ago, something the size of Mars slammed into our young planet. The impact was so catastrophic it vaporized rock, ejected debris into orbit, and eventually formed the Moon. It also, almost certainly, affected Earth's axial tilt. We don't know what that tilt was before the impact. We don't know what it would have been without the Moon's stabilizing gravitational influence. Computer models suggest that without our oversized satellite, Earth's tilt could have wandered chaotically over millions of years, swinging from nearly 0 to over 50 degrees, producing climate chaos that might have prevented complex life from ever evolving. The Moon didn't just give us tides and poetry. It may have given us stability. Dr. Jacques Lascar at the Paris Observatory has modeled Earth's axial evolution extensively. His simulations show a narrow path through gravitational chaos, a path we happen to walk. Earth's current state is not inevitable, he observes. It is one outcome among many possible histories. We are here because the dice rolled in our favor. But the dice are still rolling. Earth's tilt isn't fixed. It wobbles slightly over 41,000-year cycles, enough to trigger ice ages. The moon slowly recedes from us, 3.8 centimeters per year, gradually weakening its stabilizing grip. In billions of years, long after the sun has begun its expansion toward red giant, Earth's tilt may begin to wander. We are not permanent. Our gentle seasons are not guaranteed. The same cosmic forces that created Uranus's endless rolling could, given enough time, claim any world, including ours. Stand outside tonight, if you can find a patch of sky away from city lights. Look up at the stars scattered across the darkness, each one a sun, many hosting planets, some of those planets spinning at angles we cannot yet measure. Worlds where dawn comes once a century. Worlds where the sun spirals overhead for decades before plunging below the horizon. Worlds locked forever with one face burning and one face frozen. Now feel the ground beneath your feet. This planet rotates once every 24 hours. This planet tilts at an angle that gives you spring, summer, autumn, winter. This planet wobbles gently enough that ice ages come and go without sterilizing the surface. You exist because of that tilt. Your ancestors survived because of that rotation. Every harvest, every migration, every seasonal rhythm encoded in your biology traces back to one simple fact. Earth spins the right way, not because physics preferred it. Not because some cosmic designer arranged it. But because in the chaos of planetary formation, in the violence of ancient impacts and gravitational storms, our world emerged with the geometry needed for complexity. We are the accident that worked. So where does this leave us, you and me, standing on our improbably tilted world, staring up at the stars, perhaps with questions worth sitting with. If Earth's habitability depends on such precise conditions, how should that change the way we treat this planet, the only confirmed home for life in the universe? When you look at the moon tonight, can you feel gratitude for a cosmic collision that happened before continents existed, knowing that impact may have given us the stability we needed to evolve? What does it mean to live on a world that could have been Venus, that could have been Uranus, but wasn't? And if sideways worlds are common throughout the galaxy, does that make Earth more precious, or does it suggest that life, somehow, finds its way regardless? Uranus keeps rolling through the darkness, patient and silent. Venus spins backward, shrouded in acid clouds, keeping its secrets. And somewhere out there, orbiting stars we haven't named yet, other rotisserie planets tumble through space, some perhaps harboring life adapted to conditions we cannot imagine, others barren and frozen and burning all at once. The universe is still calling. It calls through every telescope pointed at distant worlds. Through every simulation modeling ancient chaos. Through every question we haven't yet learned to ask. The story of tilted planets isn't finished. It's barely begun. If these kinds of conversations stay with you, if you find yourself looking up at the night sky a little differently now, if you want to keep exploring the cosmic questions that remind us how improbable and precious our existence truly is, then perhaps we'll meet again, same darkness, same stars, Same wonder. Until then, remember what Uranus taught us. The universe doesn't owe us gentle seasons. It doesn't owe us stable tilts. It doesn't owe us anything at all. And yet here we are, on a world that spins just right, orbiting a quiet yellow star, aware enough to ask why. That awareness is the rarest thing in the cosmos. Use it well.